Welcome to the channel to Irrational. I'm Pranay Sharma, and in this video we are going to discuss the solutions of CS1 paper A conducted by IFoA Institute in April 2023. We are going to go through the detailed explanations of the solutions, but if you want the solution sheets, I will leave a number below in the description where you should WhatsApp, Telegram, or just message your email ID and ask for CS1 sheets, and we will email you the same. If you find any mistakes in my solution, do leave a comment. I'll go through it and I will pin the comment. Now let's get started. Question number 1. Two independent random variables x and y have the densities f of x is lambda square x e raised to minus lambda x. That seems to be a gamma distribution with alpha as being 2, right? We have lambda raised to alpha, x raised to alpha minus 1. So seems alpha is 2 and lambda is lambda, and y is lambda e raised to minus lambda y. So either that can be a exponential distribution or gamma distribution with alpha as 1. Okay. The random variable z is defined as the sum of x plus y. Identify the distribution of y with its parameters. So actually it can be an exponential or a gamma distribution with 1 comma lambda, right? And identify which one of the following expression gives the probability density function of z. So for y you can write either gamma 1 comma lambda or exponential lambda, and for x it's going to be gamma 2 comma lambda. Therefore z becomes gamma 3 comma lambda, and it's the second option or the B option which would be correct. We'll have lambda raised to alpha, alpha being 3, by gamma alpha, that would be 2 factorial. 2 factorial becomes 2, and then z raised to alpha minus 1, therefore z raised to 2 and e raised to minus lambda x. This is the option B. Let's go to question number 2. So question number 2, two friends are chatting on social media platform. The first friend has a typing speed equal to 3 messages per minute, while the second friend has the typing speed of 2 messages per minute. The process of writing the message for each of the two friends is modeled with Poisson process, and these processes are assumed independent. Calculate the probability that only 2 messages in total are exchanged between the two friends during the first minute. So we have Poisson process. So we'll say x follows Poisson 3, y follows Poisson 2, and we are talking about z, that would be x plus y, makes it as Poisson 5. So probability that z will be equal to 2 gives us 0.084224. Very straightforward. Let's go to question number 3. Question number 3. An actuary determines that the claim size for a certain class of accident is a random variable x with the moment generative function given as this. Determine using mxt the standard deviation of the claim size for this class of accidents. So here, just by looking at the mxt, you should be able to recognize that this seems to be a gamma distribution where alpha is 4 and lambda seems to be 1 by 2500. It's not useful in the question, but you should be able to recognize it. So we have mxt, I've converted into cxt, that is log of mxt, and then we'll differentiate it 2 times. So differentiate once, differentiate twice, and then we'll put t is equals to 0. We get this much. We take root and we'll get standard deviation as 5000. Now because you recognized it as a gamma distribution, it may be helpful. Gamma distribution will have alpha by lambda square, that is our variance. So that's just going to be 4 into 2500 square, and you'll take root of that and you'll get 5000. This is good for at least making sure that we have done it correctly. Let's go to question number 4. Question number 4. Statisticians A and B obtain independent samples x1 to x10 and y1 to y17 respectively, both from a normal distribution with the expectation mu and variance sigma square, with both mu and sigma unknown. The variance sigma square can be estimated by the sample variance of each sample denoted as S square X and S square Y. Identify which one of the following option gives the correct probability of S X square exceeds 1.5 times sigma square. So because X and Y both follow normal distribution are n minus 1, S square by sigma square would follow chi square n minus 1. And because S had n as 10, we get 9 S square X by sigma square follows chi square 9. So accordingly, we'll say probability S square X greater than 1.5 sigma square. I'll divide by sigma square and multiply both sides 9. So we get chi square 9 greater than 13.5. I've used R programming to find this value and we get 0.14126. And because this was MCQ, we don't have to write any of this explanation. We just have to write the option. So the option A was the correct answer. Then second part, calculate the probability that SY square exceeds 1.5 sigma square. Now here we'll have to show the probability. So same thing, we'll have n minus 1 sy square by sigma square. N minus 1 here would be 16 and chi square again n minus 1, that is 16. So probability sy square greater than 1.5 sigma square, divide by sigma square, multiply by 16 and we'll get chi square 16 greater than 24, that is 0.0895. Again I've calculated this from R. You can go through the table book and give an approximate answer as well. Let's go to question number 5. Question number 5. Two people are playing a game together involving the toss of a single coin. The coin used is biased so that the probability of throwing a heads is an unknown constant h. It is known that h must be either 0.35 or 0.85. Prior belief about h are given by the following distribution. So this is a prior belief. And we have the coin is tossed 15 times and 9 heads are observed. So we are talking about a binomial distribution here. That's the sample. Determine the posterior probabilities for the possible values of h. So here is our prior distribution given. We'll calculate the likelihood. We'll say probability x equal to 9 given h is 0.35. Because it's a binomial distribution, I'll have ncx theta raised to x into n 1 minus theta raised to n minus x. The same thing I'll do for h being 0.85. We get these values and we'll calculate probability that x will be equal to 9 irrespective of whatever the h value is. So by using law of total probability, this is the value that we get. So the posterior distribution, we'll say probability of h given x is equals to 9 would be probability of h into probability of x is equals to 9 given h upon probability of 9. Substitute these two values, you will get the posterior probabilities of h. So for 0.35 we have 0.84018 and for 0.85 we have 0.15982. You can calculate one and you can do 1 minus for the other as well. Let's go to question number 6. For question number 6, an analyst concludes from an empirical study that the number of children's x per family in a certain region has the following distribution. When asked for the expected number of children per family, the analyst claimed that an exact value cannot be calculated for the expectation, but that the lower limit can be provided. Explain whether the analyst is right. So if we see the distribution here, we have more than 3. We don't know the exact value of that. That is why we'll get a lower estimate. So to explain that, I've written as the exact value of number of children that are more than 3 cannot be determined, the analyst claims that an exact value cannot be calculated for the expectation, but that a lower estimate can be provided is correct. And I have given a few explanation points here as well. If the maximum possible number of students were known, then an average between 4 and the maximum number of students could be taken for more than 3. As the maximum possible number is not known, lowest estimate 4 will be taken. Second part, calculate the lower limit for expected value of x, the expected number of children per family in this region. So summation x into probability of x, last greater or equal to 3, I have taken it more than 3, I have taken it as 4. One more way could be that we might take more than equal to 3, that means 3 plus, and we could take this 0.13 probability for 3 itself. That can be another approach where rather than taking the minimum value there as 4, we can combine it with 3 and take that. Slightly different answer, and I'm expecting them to give you full marks for both of these approaches. Then for the third part, we have from a future study of families with more than 3 children, it is concluded that the conditional expected value of x greater than 3 is 4.5. Identify which one of the following options give the expectation of x. Here, because we have options, we will not have to show the solution, just write the option. Now, because for our conditional probability, we know a given b is nothing but probability of a intersection b into upon probability of b. So a intersection b would be conditional into probability of b, and our expected value of x given x is greater than 3 would be nothing but summation x into probability of x given x is greater than 3. This would go from x being 3 to infinity. That would just be summation for all values of x into probability of x upon probability x is greater than 3, and here we'll just say x is going from 3, actually not 3, this should be from 4 to infinity. Again here this should be from 4 to infinity, and we want just this part for our expectation. So it would be expected value into probability greater than 3, that is this part. And for the rest, I have 1 into 0.05 probability of 1, 1 into probability of 2, 3 into probability of 3, and this would be summation of values of x into probability of x from 4 to infinity. So the value we get is 1.325. That is option D. Let's go to the next question. Question number 7. Let x1 y1 to xn yn be pairs of random variables with each pair xi and yi being independent of all other pairs. The distribution of x is normal distribution, standard normal actually, 0, 1, and the conditional distribution of y given x takes a particular value xi is normal xi into theta, 1 for I going from 1 to n, where theta is between minus infinity to plus infinity is an unknown parameter. Identify which one of the following option gives the correct expression of the likelihood function. So because theta is going to be dependent on the values of x as well as y, we would have to take the joint distribution. For joint distribution of x and y, again using conditional probability, we'll say it is f of x into f of conditional y. So that is what we'll be using here for the likelihood. We'll substitute the density of standard normal distribution, and this is for normal distribution, and then combine them together. We'll get this, and that is nothing but option B. For the second part, determine the maximum likelihood estimator theta hat of theta. You don't need to check that your solution is maxima of the likelihood function. So we have the likelihood. I have taken pi inside, that would become summation, and the constants I have removed it. Log likelihood, remove the exp, then differentiate. We'll get summation x into y minus x into theta. So that becomes nothing but summation xy minus theta times summation x square, and therefore theta hat becomes summation xy upon xi square. This is basically the formula of beta hat for a linear regression, where we get sxy upon sxx. Here mean of x is 0, that is why it has been reduced to summation xy upon summation x square. Third part, determine the Cramer-Rao lower bound for theta hat, and fourth part is write down the asymptotic distribution of theta hat. So for Cramer-Rao lower bound, we'll have to double differentiate. We are left with just minus of summation xi square. We'll take expected value. Expected value of x square is going to be variance of x minus expected value of x square. That just turns out to be 1, because expected value of x square is 0 and variance of x is 1. So we'll get summation of 1, that is n. So CRLB becomes 1 by n, and therefore the asymptotic distribution theta hat follows normal distribution with theta comma CRLB will give us this value. Let's go to the next question. Question number 8. A space rocket contains 6 identical mechanical components that work independently of each other and need to be in operation for a successful launch. Data from simulated launches are available to establish the relationship between the number of damaged components y on the rocket and the air temperature x in degree Fahrenheit. It is suggested to analyze the simulated data using a binomial generalized model with the canonical limit function, where y follows binomial 6, p. P is the probability of a component being damaged, and a linear predictor has the form of beta 0 plus beta 1 x. The analysis of the simulated data gave the following estimates for the model. So we have estimate for beta 0 and beta 1, and we have standard errors. Determine whether air temperature significantly affects the number of the damaged component on the rocket by computing a suitable p-value. So for that we have to figure out whether beta is significantly different from 0. So our hypothesis, beta 1 is equal to 0 versus beta 1 not equal to 0. Test statistic, we'll take beta hat 1 minus beta 1 upon the standard error follows a standard normal distribution. The statistic is going to be minus 4.064, and p-value would be very small. So as the p-value is very small, we have sufficient evidence to reject H0. Air temperature significantly affects the number of damaged components on the rocket. Second part, estimate to do decimal places the probability that a component will be damaged when the air temperature is 31 degree Fahrenheit. So we just want to find the estimate for P. At 31 degree, we'll substitute the beta 0 and beta 1 to find out the linear predictor, and we'll use the link function to find our mu hat value. So that becomes 0.99. That is nothing but the estimate of P hat. Third part, estimate the expected value of the number of components that will be damaged when the air temperature is 31 degree Fahrenheit. Now we have the estimate for probability. All we have to do is multiply 6 to it to get the estimate. So n into p hat gives us 5.94. That's the estimate of the expected number of components being damaged at 31 degrees Celsius or 31 degree Fahrenheit. For the next part, it is believed that the launch is safe when at least 5 of these 6 components are not damaged. 4a, calculate the probability that the launch is safe when the air temperature is 31 degree Fahrenheit. So we have just taken the p hat value and calculated the probability that y is less than equal to 1, because that is the probability of component being damaged. So it's a very small probability. So the conclusion, the probability of at least 5 components not damaged is practically 0, and hence it is not safe to launch. For the fifth part, a second approach for analysis, the simulated data was suggested, where a logarithmic link function would be used with the same GLM as used before. Comment on the suitability of the second approach. So logarithmic link function will give the range of mu as 0 to infinity, whereas the range of p is 0 to 1. Hence the logarithmic link function is not a good suggestion. Let's go to the next question. Question number 9. An insurer models the number of cars owned by a single policyholder as a discrete random variable with the following distribution, where p is an unknown parameter. In an empirical study, the number nk of policyholders owning k cars is recorded for k 0, 3, and n4 is the number of policyholders with more than 3 cars. First is identify which one of the following function is a log likelihood function for p using recorded numbers n0 to n4, where c is a constant independent of p. So for likelihood function, we'll directly take the probability raised to the frequency for each one of them. Then you can remove the constants, because again it's just constants. So proportional, we'll have p raised to n0, n1, n2, n3 all added together, and we have 1 minus 2p raised to n4. So log likelihood n0 plus till n3 log of p plus n4 log of 1 minus 2p. That is option D. Second part, derive the maximum likelihood estimator for p. You don't need to check that your solution is the maximum likelihood function. So we have our log likelihood, differentiate that with respect to p and solve it. We get p hat as n0 to n3 upon 2 times n0 to n4. For the third part, in a large study, the insurer has to restrict the information held for each policyholder due to data protection. The insurer records only the number of policyholders with no cars, that is M0, and the number of policyholders with at least one car, that is M1. So this is a binomial style question now. Show that the log likelihood function for the parameter p based on the observation M0 and M1 and the above distribution for the number of cars is given by this. So M0, that is 0 number of cars, probability is 1 by 2 p, and the rest would be M1. So that would be 1 minus of this 1 by 2 p. So for log likelihood, we'll have theta raised to the M0 value and 1 minus theta raised to M1 values. And I've just simplified this. We'll get 2 minus p upon 2. Taking log, we'll get M0 log of 1 by 2 p plus M1 log of 2 minus p. That is what was asked. Fourth part, identify which one of the following estimator is the maximum likelihood estimator for the parameter p. So we'll differentiate and we'll find the p hat. So now differentiate this, we get this, and simplify it, equate it to 0, simplify it, we'll get p hat as 2m0 upon m0 plus m1. Next we have the following data have been observed. They have given us n0, n1, n2, n3, n4. Estimate the value of p hat using the estimator derived in part 2, and the sixth part is estimate the value of p using the estimator found in part 4. So see, n0 is also going to be m0, and if we add all of these, I think we have 130. So m1 will just be 130 minus 50, that is 80. So we'll substitute in both of them. We get p hat for the fifth part as 0.4615 and for the sixth part we get 0.76923. Let's go to the last question. Question number 10. A banking analyst is assessing the performance of a newly developed credit risk model against experts' knowledge. The credit score produced on a sample of 12 customers by the expert X and the model Y are the following. A, fit a linear regression line of Y on X. Second part is calculate the Pearson's correlation coefficient between the experts and the model's score. So the first thing I did was calculated X bar and Y bar. Use that to calculate SXS, SYY and SXY. Then we get the beta hat and the alpha hat. All of these formulas you can take that from the table book. So the linear regression line we'll have y hat I as alpha hat plus beta hat xi. Then Pearson's correlation coefficient R is going to be sxy upon root of sxx into syy. So that is 0.829802. I have used the formulas here using x bar and y bar. If you are using summation x by n and then solving it, summation x by n and summation y by n, you will get slightly different answer because of the number of decimal points that we are taking. So if your answer is slightly different from mine, don't worry, it will be accepted. Third part, perform a statistical test using Fisher's transformation to determine whether the population Pearson's correlation coefficient is significantly different from 0.8. Your answer should include the p-value of the test. So H naught would be rho equal to 0.8 versus rho not 0.8. For Fisher's Z transformation, we'll calculate ZR and Z rho. That would be tan H inverse of R and tan H inverse of rho. And this becomes our test statistic. We'll have ZR minus Z rho upon under root of 1 minus n minus 3. 1 by n minus 3. Okay. That follows the standard normal distribution. So statistic is 0.667 and the p-value is going to be 0.7897. So we can say even at 70% level, we have insufficient evidence to reject H naught. Rho is not significantly different from 0.8, or you can say rho is equal to 0.8. Fourth part, construct a 99% confidence interval for the slope parameter of the linear regression line fitted in part 1. So slope parameter, that means we are talking about beta. So we'll calculate sigma hat square, that is 0.777, and we'll use that to calculate the confidence interval for the slope parameter, that is our beta. So beta hat plus minus t of 0.5%, n minus 2 is going to be the degree of freedom, and this is the standard error, root of sigma hat square upon sxx. So the confidence interval is 0.15 to 0.77169. Fifth part is comment on your answers to part 3 and 4. Now this is a little bit tricky part because in part 3 they are talking about the correlation coefficient, whereas in part 4 they are talking about the slope parameter. So if you just say in part 3 we saw that rho was 0.8 but it does not lie in the confidence interval, you will be wrong because they are not the same thing. So from both of them we can only comment about the relationship. So we'll say part 3 concludes that the correlation coefficient is not significantly different from 0.8, and part 4 shows that even at 1% level that the slope parameter is significantly different from 0. From both of this we can conclude that there is a positive relationship between the credit score produced on a sample of 12 customers by the experts X and the model Y. So if you compare the value, you will not get any marks. What you had to compare was both are suggesting that we have a positive relationship. That's it. Then we have the analyst is informed that the score on their own are not the most important aspect of the model. Instead, the performance of the model is assessed by how well it is able to predict the rank order of the 12 customers provided by the experts. A higher score corresponds to a better customer. The ranking of the customer based on their above score are provided in the table. Calculate the Spearman's rank correlation for the data between the models and the experts score. For Spearman's rank correlation, we'll have to take the difference in rank for each one of them and square them. So I have the DI square. Addition of that, we get 72, and our RS, that is 1 minus 6 times summation DI square upon n into n square minus 1 gives me 0.74825. Comment on the model's alignment with the expert's opinion based on your result from part 2 and part 6. So you'll have both Pearson's and Spearman's correlation coefficient suggest that there is a strong positive relationship. As Pearson's coefficient is higher than the Spearman's, implies that the scores are better correlated than the ranks. As the prediction of rank is the most important aspect, the model is averagely adequate in it. That completes our paper here. Overall, the paper was very simple, very straightforward. Maybe there was one or two places where you had to think about the question a little bit. Otherwise, there was nothing new in the question. Most of you would have completed the paper much before the time, that is 3 hours and 20 minutes. It took me about 2 hours and 30 minutes to complete the paper. Looking at both paper A as well as paper B, it seems like the passing mark will be high this time, maybe about 56 to 58. And I wish all of you would have passed that mark very easily. If you find any mistakes, do comment. I will pin that comment. I'll be making the paper B solution in maybe 2 days. So do subscribe so that you get the notification. Like and share if you find this helpful. And I will see you in the next one.